Hey everyone, so I just want to go through this next section, just getting some foundational stuff before we get into the actual meat and potatoes of this unit, which is all going to be about units and conversions. So I just wanted to make a quick little comment on this. So as you know, units are used to kind of give an idea of scale for our measurements. If we want to find the height of something, if we say feet, that's different than if we said inches. You know, it kind of gives an idea in the mind. Units really are important for just everyday life. And as cultures start to interact with each other, um, there ended up being a little bit of confusion with units. See, it turned out most cultures, in the early days at least, tended to use their own body parts or natural things within the area as their units. So, for example, um, they could use a rod to measure distance, and that would be a standard rod within the community. Or they might use their arm or their hands to figure out how long things are. This makes sense since a lot of times, again, in the early time, they didn't really have access to a whole lot of technology in order to make measurements, but they would still need it in order to actually do stuff. Obviously, as these communities started to interact with each other, though, this started to come with problems because one civilization might use a measurement that another one didn't. So there had to become a more consistent unit system. Now, the first one that actually came about was well, there's two main unit systems now. There's the US customary units, which is the ones that we use, as well as a few other countries, and then there's the metric system. Now, the countries that use the US customary system are the United States, Liberia, and Burma. There are some countries that kind of do like a pseudo combination. As far as I know, I believe it's England and Canada kind of use some units within the US customary system and some within the metric system. In fact, this system actually is originally called the imperial system because it originated from England. Um, Now, for example, a good idea of kind of what I said before about taking measurements from the body. Um, for lengths, we have an inch, a foot, and a yard. Well, where do these numbers come from? Well, an inch comes from the width of the king's thumb. The foot was defined as the length of a king's foot. And before anyone thinks that the yard is the size of his yard, it was defined as the length between the king's nose and fingers. Now, there was a main problem with this. Every few decades, the king changes. Sometimes they may change within a year or two, which means the inch, the foot, and the yard would be constantly changed every few years. So at a certain point, they kind of fixated, the definitions for this. For example, the foot was defined, and then an inch is actually the word inch comes from a twelfth of something. So a twelfth of a foot, and the yard is again defined as three times a foot. So a lot of this kind of they start to interact with each other. One of them is defined as something, and then the other ones kind of come from some sort of mathematical relationship to the others. But it also explains why the conversions are really weird. Now, there are actually a lot of other weird units that you may not have known through the customary units. There's a rod, furlong, acre, oxgang, virgate, caracat, chain, stone. These are all units within the U.S. customary units. They're not commonly used. Usually they're used for a very specific reason, but you won't really need to use it. Now, it's interesting to note just these weird conversions, like 5/2 a yard and 1/8 of a mile and 43,560 feet, 15 to 20 acres. I mean, what type of unit is something that's, a range of numbers? So, as you can see, the U.S. customary units are very complex. Their conversion factors are so awkward. Because of this, we end up using the metric system in science. It's used by pretty much everyone else. Um, and the way it works is that you have a set of fundamental units, and then every other unit for that set of measurements is just going to be a power of 10 greater. So all you do is add or remove zeros to get to different levels. So for example, a meter is the fundamental unit for length, and then we could have kilometer, centimeter, millimeter. All it is just taking that number and moving the decimal place over a certain number. So if you want to convert between all these different units, you're either multiplying or dividing by some power of 10. Um, Now, the fundamental unit for mass is actually a gram, but in this class, we're going to be considering kilogram as the basic unit. This is actually called standard unit or SI units. Um, but yeah, then we have time being in seconds, and then electric current is amps. So again, these are all fundamental units. These are units that are defined, and then every other kind of unit is based off of that. Now, there are other types of units. There's things called derived units, which we'll see later on, which is basically combinations of these. So, for example, speed is measured in meters per second. That's its derived unit. Acceleration is meters per second squared. Newtons is the unit for force, but again, it's a derived unit. It's made up of the meters, the kilograms, the seconds. Energy is measured in joules, so on and so on. Now, this is given on the Regents reference table. Um, and basically, we have these prefixes that get added on to a measurement. And again, it just scales the number up and down by some factor of 10. So if we have a megameter, that would be equal to 1 million meters or 1,000 kilometers. Again, all you're doing is adding, subtracting zeros. Some common measurement tools that you should recognize. I'll just go through this really quickly. We have rulers that are used to measure length and distance. They come in all different measurements, but we're mainly going to be using it as meters. Any ruler in our class should be measuring in centimeters, regardless of what unit it says it's measuring. Obviously, if it looks like it's an inch ruler with the uneven lines, and it's inch, but I just want to clarify that no ruler in the classroom measures anything in metric besides centimeter. There's no millimeter ruler, there's no meter ruler. It's all measuring centimeters. We have watches and clocks that measure time, typically in seconds. We have triple beam balances that you'll see. This is used to measure mass. Now, this is actually important to note. This does not measure the weight of an object. It measures mass. I know I put here that it can measure pounds, but that's because pounds is really weird. It sometimes measures mass, sometimes it's weight. Now remember, mass is the amount of matter something has. Again, it is not weight. I'm going to hammer this in when we get to the force section. Then you also have radar guns. We're not going to be using a lot of these things in this class, but when you go to derive or when you go to plan out and come up with these lessons and lab procedures, you're going to want to kind of keep track of all these different things you can use to measure the speed and the time of objects. So guns measure speed, again, typically meters per second as far as we're concerned. Then they have these things called photo gates. I don't think that we're going to be using them in this class. Now, their main goal is to actually measure time. The way it works is that there's a little laser beam that goes between here, and it'll measure the time that the beam is broken. Now, this could actually be modified using a program to also measure length and speed with few modifications. So keep this in mind. Again, when you're going to do your, planning out lab questions, keep in mind that you have these photo gates that can measure very accurate moments of time. And again, seconds and minutes it could be measured in. Chances are you're probably not going to use these next ones, so I'm just going to go through them quickly. Thermometers measure temperature. In this class, we would use either Celsius or Kelvin, which isn't appeared. Again, I shouldn't have said in this class. That's actually more like AP Physics 2. Then we also have these things, graduated cylinders, which can be used to find liquid volume. It could also be used to find solid volume as well. Typically, you're going to see it measuring liters and milliliters. All right, so scientific notation is huge in the metric system. As I said, conversion between the different units is a factor of 10. So that means you're going to need to know about the scientific notation. Again, going to breeze through this real quick. As you know, scientific notation measures things that are really, really big, really, really small. It's a really nice way of kind of condensing numbers. You would not believe how small and how big some of the numbers we do in this class. For example, the mass of an electron is 9.11 times 10 to the negative 31, which basically means that it would be a decimal, 30 zeros, and then 911. That would be really painful to have to write multiple times in a calculation. So scientific notation makes this entire setup really easy. The layout of the scientific notation is that there's a base number and then there's a magnitude factor, sometimes also called order of magnitude. So if we have a number that looks like this could be rewritten as 1.546. This would be our base, and the 12 being the magnitude factor. Keep that in mind. If they ever ask, like, what's the order of magnitude, um, not just the word magnitude, order of magnitude, they're referring to this exponent because it's just telling you how many decimal places there are. And yeah, as you know, this number, this order of magnitude, the magnitude factor, whatever you want to call it, basically tells you how many times you're moving the decimal place. So if you're going between standard number, scientific notation, anything in between, that exponent is telling you how many times you're moving the decimal. If the decimal is a positive number, the number is a big number, so you'd be moving the decimal place over to the right to get rid of it. Um, if this was negative, then the number's small, so the decimal will be in front of the base, things like that. Now, one thing that actually can be a good lifesaver is to remember some simple math tricks, algebra tricks, when you're dealing with scientific notation in math. The reason I'm pointing this out is you guys have calculators. You have graphing calculators that allow you to do the division in a fraction form with a numerator and a denominator. I do recommend doing that, but for some people that it might take too much time. You need to be very careful when you divide numbers in scientific notation because if you don't plug it into the calculator properly, the calculator will misread what you're going to do and your exponent at the very end is going to be off. So, a lot of times, what I recommend is when you're doing math with scientific notation, try to very quickly figure out what the order of magnitude should be based off of these rules. Like, for example, when you multiply scientific notation, if you're going to do it by hand, you multiply the bases and add the exponents. So, right off the bat, I can see that my exponent should be somewhere on the order of 13 because 5 plus 8 is 13. So it might be 14, might be 12, but it should be somewhere around 13 plus or minus 1. Now, if I do the math for this and I do 4.2 times 6.1, I end up getting 25.62 times 10 to the 13th. This is not proper scientific notation since the base has to be less than 10. So I move the decimal place over one more time. And I add 1 to the exponent. So it becomes 2.562 times 10 to the 14th. When you're dividing, again, you divide the bases. This time you're doing the opposite of what you did before. You're going to subtract the exponents. Again, when I plug this into the calculator, I should expect to see 5 minus 8, an exponent to the negative 3. If I don't get an exponent to the negative 3, then I know I did my math wrong. So again, or not that I did my math wrong, but the way it was plugged into the calculator was incorrect. So when I do this work, I should end up getting the number 6.89 times 10 to the negative 4. So again, I estimated that would be negative 3 plus or minus 1 gets me negative 4. So this tells me that my number makes sense. And that's pretty much it. So again, that's all about measurements and scientific notation, very basic stuff. Just want to get that out of the way before we move on to the actual physics stuff. All right, if you have any questions, let me know. Otherwise, good luck and have a great day.